Okay, so this is a slightly different problem than we've worked previously. In this problem here, what I have is I have some box here, some block, and it's on some frictionless surface. And there is some, not necessarily energy, not necessarily a force that's pulling it back and forth, but in this case, we're given energy. It's a function, so energy, then U, of course, is potential energy. Potential energy as a function of x is equal to 0.630 x to the fourth. So what that means is as this block moves, let's say your origin point is here, x equals 0. So as you move this way, the energy is going to increase, or if you went this way, decrease. Or if you go this way, it's going to increase. So the energy is going to increase if you go this way, or if you go this way, or conversely decrease if you go this way, decrease if you go this way. That's the energy as a function of displacement. So as you displace this thing, your energy will change. Okay. Now, what I want to know is what's the force on this block when it gets displaced negative 0.8 meters away. So when this thing moves, let's say here, negative 0.8 meters away, yeah, I could find the energy, but obviously by just plugging in negative 0.8, right? That just goes into x, boom, and I have my energy in what? Joules. So I could find the joules at negative 0.8 meters displacement, but I want to find the force, of course, in newtons. Now, before we do this, I want to talk about something I probably haven't mentioned before, which is, now let me give you an example. So let's say there's a person here, right? So here's some person, and they throw a ball up, right? So here's some ball, and they throw it up like this. So what's happening here is there's gravity, right? Gravity is going to try to pull this ball down. But as the ball is going higher and higher, what's happening to its potential energy? It's going up. So the potential energy in the ball is increasing as it goes up. But where's the force at? What force is acting on this ball once it's left his hands? What force is acting on this ball? Only gravity, right? Only gravity. And so what's gravity doing? Gravity is pulling down in the opposite direction. So gravity is doing negative work. Gravity is doing negative work. As the potential energy gets bigger, right? As it gets bigger, gravity, of course, is pulling down on this thing. So you can see that force and energy are kind of like opposites. When this thing wants to go up, force is like, or gravity is like, no, you got to come down. So so as this energy is increasing, the force is like, no, you got to come down. Conversely, it's just like a spring, right? So if you had a spring and you try to push it in, let's say you try to push in a spring, right? You're going to increase your potential energy, right? Because the energy is being stored in the spring. So your potential energy is going to increase. But what's the force, though? If you could feel the force on the spring, where does the spring want to go? Well, the spring wants to go in the opposite direction. So as you push in, as the potential energy is increasing because it's actually moving in, the force on the spring that it feels, it wants to go in the opposite direction, okay? Conversely, if you had a spring again, if you had another spring like this, and you were stretching it, yeah, you're going to get more and more potential energy as you're stretching it. But what does the spring want to do? It wants to pull you back. So in these cases here, whether we talk about springs being compressed, springs being stretched, or gravity, these are called conservative forces. Okay. Work and energy are opposites, okay? Because gravity, for example, here, when the potential energy is going up, when this thing is going up, right? Right, when this thing is going up, yeah, the potential energy is increasing, but the work due to gravity, because gravity is pulling down, then the work is negative, right? So if this is going up, then the work is negative. If this way's here, your potential energy is increasing, but it's trying to pull in this opposite direction. So it's, once again, the work is negative. So what I'm trying to say is that the work done is the negative of the change in U, or the potential energy, and this is conservative energy, okay? Right, because remember, when you're trying to go up, when something is going up, yeah, his potential energy is increasing, but the actual work due to gravity, that's negative work. That's negative work because it's going against the going against the displacement. Okay, so that's cool. So what is work? So what is work? Well, work is just a force times the distance, right? So let's just do the x-axis here. So we'll say the force in the x direction times a change in x. Okay, that's work, right? Work is this. It's force times displacement. So I just changed W to F delta x is equal to negative change in potential energy. Now what I can do is I can divide by change in x. And so now I have the force in x is equal to the negative delta U over delta x. And of course, this is over some long duration, but you could actually make it instantaneous by just doing the instantaneous rate of change, and just say f of x, the force in the x direction, is the negative change in U over change in x. Okay, so this is basically what I was just saying before. If something is going up, yeah, his potential, his energy is increasing, but the work due to gravity is negative, okay? And so what this is saying here is that your force, remember before Newton's second law, force is equal to mass times acceleration. Here, this is another way of defining force. Instead of using Newton's second law, F equals ma, you could just say force equals the negative gradient, okay? So let's say, I don't know, let's say I have some graph here, and then I have some gradient, right? And let's say this is du dx, right? And let's say this gradient is, I don't know, 3x or something like that, right? 3x. Well, then the force is opposite of that. Then the force would be negative 3, right? It'd be negative 3. Well, because your slope here is just the slope here is actually just 3. So if that's your slope, then the force would be negative 3. In this case here, it would be in newtons, right? So force, instead of force equals ma, which is Newton's second law, there's another way to define force, and force is just equal to the negative energy gradient. Okay, so the change in energy over displacement. Okay, so what we're going to do is we're going to use these to solve this problem. So you may remember that I had this function u, which is potential energy, as a function of displacement, was equal to 0.630 x to the fourth, right? Now, if I were to plot this thing, let's draw a graph like this. I'm going to change colors to maybe something like this. Okay, and so this is u of x. U of x looks just like this. So what this means is as you are displacing from the center point here, from your origin, as you're displacing, the energy is what? Going up and 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 up. It's increasing. Or if you go this way, the energy is increasing. It's like a spring, right? It's like a spring. If you stretch the spring, your potential energy is going to increase. Or if you compress the spring, the potential energy is going to increase. Or think of it like gravity. As you move up and up and up and up and up, this way, this is up, this is up, your potential energy is going to increase. Conversely, if you go, let's imagine you're in Earth and imagine you're going straight up, and this is like, you're on the Earth, you're like the opposite hemisphere, you're below the Earth, but you're going down, then you're also increasing your potential energy, right? Let me just show that in case that was a little confusing. So, let's say this is let's say wrong one. Let's say this is the Earth, and this is the center point. Yeah, your potential energy is going to increase if you go this way, and you're just going to increase if you go that way, right? That's what I'm just saying. Okay, so that's cool. Now, what I want to do is I want to find the force. So to find the force, I need to find. Remember, I want to find the force in the x direction as a function of x. Obviously, is equal to the negative gradient, which is du dx. So basically, I just need to find the derivative of this function. So d dx of 0.630 x to the fourth. You bring 4 down, right? Before you bring 4 down, times 0.630, and then x to the third. And once you do that, you have 2.52 times x to the third. Okay. Yeah, and so, but this ends up being negative because so this number is positive, right? If you just took the derivative of 0.630 x to the fourth, yes, this number here is actually positive, but we want it to be negative because force is equal to the negative of that, the negative gradient. So this is f of x equals that. Okay, and so then that's it. So if you were to plot this function right here, negative 2.52 x to the third, it would look like this. Let's change it to maybe this color. You get this, come down here, and then it looks something like this. And this is f of x. Force as a function of displacement, okay? That's that. And obviously all you'd have to do in here if you want to find the actual value, you'd say what is f at negative 0.8. Okay, this number here becomes this number ends up being a negative because it's a negative cubed, and so if it was squared it'd be positive, but if it's cubed it's going to be negative. So this is going to be negative, and then this is a negative, so a negative and negative is a positive, and you would actually end up with equals 1.29 newtons. So the force at this point here is a displacement of this right here of negative 0.8 is 1.29 newtons. Okay. Now, let me sort of show what this graph means. What this graph means. Once again, this the red curve means energies. Think of it like if you want to, think of it like a spring. So as the spring is stretched this way, the energy is going to increase. If the spring is stretched this way, the energy is also going to increase. Either way, you can think of like a battery, like you're charging the battery. If you stretch it, you're charging the battery. If you compress it, you're charging the battery. But what the hell does this mean, though? Why does this blue curve go up like this and down like this? What does this mean? Well, remember, that's the force. So if I am going this way, let's say I'm compressing the spring, right? I'm compressing the spring, and then so the energy is increasing. It's increasing in the spring. The potential energy is increasing. Well, what does the force want to do? What is the force trying to do? Well, you can see the force is what? It's positive, right? Because it's up here like this. The force is positive. It's getting more and more and more positive. That means this force is trying to cause the spring to do what? Move in this direction. It's trying to make the spring move in this direction. So the more energy you put in, the higher this gets, which means it really wants to go back. It because you're compressing it, right? More and more and more and more, you're super compressing the spring. It doesn't like that. It wants to go back to its natural state. So that's what it's saying here. Is it's trying to force it back. Conversely, on this side, if you stretch it, you're also going to increase its potential energy. But as you stretch it more and more and more and more, what's going to happen to this force? So now the force is negative. Now the force is negative. And so what does that mean? So that means it wants to take this displacement and move it in this direction. So the force being positive here says move it in this direction, but because it's negative here, it says move it in this direction. So either way, if it's on this side, the force says no, move it here. If it's on this side, it says no, move it here. So you can see that the force really wants to bring everything back to equilibrium, back to zero, whether it be a 0 point of gravity, 0 point as far as a spring is concerned, maybe as a battery is concerned. So anytime you have a conservative force, it always wants you to bring everything back, or conservative energy. It wants you to bring everything back to the center point here. Whether this here, bring you back to the center. Over here, bring it back to the center. Okay? And so and this works, and like I said, when you're talking about conservative energy. Yeah. All right, that's it.